Hi everyone, this is Lab 3, Black Hole in Orbits. This lab was divided into two parts. The purpose of Lab 3 observes the motion of a star orbiting a black hole to estimate the black hole's mass, and also a spaceship trying to orbit both a planet and its moon. These motions are modeled using computational models. The main goal of this lab was to understand how gravitational forces influence motion and how changes in velocity or position can drastically affect orbital stability. The motions from this lab are based on the physics principles, which is Newton's second law, also known as momentum principle, which relates to net interaction between system and surroundings. The formulas that will be used mainly consist of curving motion, gravitational force, momentum, and the other ones shown on the right. In this lab, I explored how gravitational forces govern orbital motion through computer simulations and GlowScript. In part 1, I modeled a star orbiting a black hole to calculate the black hole's mass using the relationship between force, momentum, and circular motion. In part 2, I extended the model to a three-body system, planet, moon, and spaceship, to see how multiple gravitational forces interact. By adjusting the spaceship's initial velocity, I observed collisions in a variety of orbits. The results show that a stable or figure-8 paths only occur within a narrow range of initial speeds and directions, highlighting the sensitivity and complexity of three-body gravitational motion. In part 1, I measured the star's change in momentum and force. The system, the star orbiting around the black hole, and the surroundings, the black hole, which exerts a gravitational pull on the star, and space environment beyond. Using my personalized seed, I tracked the star's changing momentum and used it to infer the gravitational force and mass of the black hole of 4e to 76 kilograms. This confirmed that the black hole's gravity is strong enough to maintain an elliptical orbit for the star. In part 2, I tested different initial velocities for the spaceship. The system, the spaceship and the moon, and the surroundings, the planet, which also exerts a strong gravitational force on both the moon and the ship. The ship's path results from both the planet's and moon's gravity, producing the complex shaped orbits. And the ship has an initial velocity vector of negative 2.5 times 10 to the fourth in the x direction and 2.6 times 10 to the fourth in the y direction, meters per second. I found that if the velocity was too small, the ship crashed into the moon or planet, and if it was too large, it escaped orbit. Only a narrow range of initial speeds and produced stable orbits. This showed how orbital motion requires just the right balance between gravitational attraction and forward velocity. There are a few similarities between both simulations. Both use Newton's law of gravitation and Newton's second law to predict motion, and both rely on vector forces that depend on distance and mass. However, they're also quite different. In part 1, the black hole star system is mostly a two-body problem, simple, and part 2, adding the moon and spaceship makes it into a three-body system, which becomes a lot more complex. The spaceship's motion depends heavily on its initial velocity, and even small changes can cause it to crash or escape. Some possible sources of error include the initial velocities. For this ship in part 2, which may have been off, it was really hard to get a perfect figure 8 orbit around the planet without having the ship crash into the moon. There was also a slight lag for the orange arrow in part 1. This could have been a numerical error in my code. Now for the questions. In part 1, one of the key takeaways is understanding the difference between net force and rate of change in momentum. The net force is what causes momentum to change. It tells us how and in what direction the object's motion will evolve. When momentum changes directions, that's related to the perpendicular component of force, and when it changes in magnitude, that is the parallel component. So observing how momentum changes over time gives us direct insight into the forces acting on the star. For the second questions, what if? If we extended the model to include a black hole, a star, a planet, and a moon, we'd have to calculate every gravitational interaction among all four objects. In reality, the black hole's force would dominate because of its huge mass, but the smaller interactions, like between the moon and the planet, would still matter for local motion. This type of system becomes extremely difficult to solve analytically, which is why the simulations are really useful. In conclusion, this lab showed that force and momentum are directly linked, and small changes in initial conditions cause big differences in motion. Part 1 demonstrated how we can determine a black hole's mass based on orbital motion, and Part 2 showed how delicate orbit stability is, and only certain initial velocities lead to stable motion. Thank you.